Have you ever stopped to think about what actually happens when you shrink a photo? Or, when you throw a filter on an Instagram post? It just feels like magic, right? Instant. But behind that screen, your computer is speaking this incredible, hidden language made entirely of numbers. So today, let's pull back that curtain. We're going to learn the language that lets computers literally see and shape our visual world.
Okay, so we have all been here. On the left, you've got this beautiful, sharp photograph. And on the right, well, that's what happens when we try to resize it the wrong way. It's just a blocky, jagged mess. Now, it's the same image, but somewhere in the translation, something went really, really wrong. And that's the big question for us today. What is it that causes that ugly pixelation? And what's the clever trick that programs like Photoshop use to make images look perfect every single time? Believe it or not, the answer is way simpler and honestly, way more powerful than you might think. All right, let's dive into section 1, a pixel-perfect problem. We're going to take a closer look at what's going on here. See, that blocky image, it comes from an idea that's logical, but it's totally flawed. To figure out the right way to do things, we've got to start by understanding the wrong way. So, to fix our broken image, the very first thing we have to do is change our whole perspective. We need to stop seeing a picture of a car and start seeing what the computer sees. And what it sees is just a massive grid of numbers.
That's really it. I mean it. Every single digital photo, whether it's a tiny icon on your phone or some stunning high-res landscape, is just a grid. You can think of it like a spreadsheet made of color. And each little tiny square in that grid, that's what we call a pixel.
And this is where we really pull back the curtain. For a simple black and white image like this one, every single one of those pixels gets a number, and that number is just a simple instruction for the computer. It tells it exactly how bright that one little spot should be.
And the rule is dead simple. A higher number, like 201, means a brighter pixel. A lower number, like 92, means a darker one. Everything else is just a shade of gray in between. This right here, this is the basic fundamental language of every digital image.
Okay, so now that we know that images are really just grids of numbers, let's look at the most obvious common sense way to make one smaller and see exactly why it's such a disaster. So the simple idea seems totally logical, right? If you want to make an image half its size, well, you just throw out half the data. You just go in and delete every other row and every other column. But here's the problem. You're not just deleting numbers from a spreadsheet, you are throwing away critical visual information.
And this is what you get. When you just carelessly toss out that information, you end up with these awful, jagged edges and blocky artifacts. There's a name for this effect. It's called aliasing, and it's the reason why badly resized images look so amateurish and, well, broken. You lose all the smooth, subtle details from the original.
I love this analogy. When you do it that way, you're treating a beautiful picture as if it were just a spreadsheet, and you're just randomly deleting cells. I mean, you would never do that with important financial data, right? So you definitely shouldn't be doing it with your visual data either.
Okay, so if just deleting pixels is the absolute wrong way to do it, what's the right way? Well, the answer is this really elegant mathematical idea called convolution. This is the secret sauce. It's the process that lets computers intelligently transform images instead of just breaking them.
So here's the key idea. Instead of deleting pixels, convolution creates new ones. It works by looking at a pixel and all of its neighbors, and then intelligently blends them together using a very specific recipe. The result is a much smoother, much more natural-looking image. It's all about blending, not breaking.
And what's that recipe I mentioned? It's something called a kernel. And a kernel is just a tiny little grid of numbers, usually a 3x3 grid. It acts like a blueprint. It tells the computer the exact importance, or you could say the weight, to give to each neighboring pixel when it's creating that new blended one.
You can kind of picture it like this. Imagine that tiny kernel matrix sliding across every single pixel of the original image. At each and every stop, it does a quick little calculation using the neighbors, and that creates one new pixel for the output image. It just does this over and over and over until a brand new image is built from scratch.
Now, this is where it gets really, really cool. Because by simply changing the numbers in that tiny little kernel, you can get completely different effects. That kernel, it's the secret recipe. It's what can do everything from resizing an image, to sharpening it, to applying some creative filter.
And you know what? The math itself is surprisingly easy. You just place the kernel over a pixel. Step 2, you multiply the value of each neighbor by the number right on top of it in the kernel. And then step 3, you just add all of those results together. That final sum, that's the value for your brand new pixel. Simple, right?
And this is the real power of that recipe. Let's say you want to blur an image. Well, you just use a kernel that basically averages out all the surrounding pixels. But what if you want to sharpen it? Then you use a different kernel, one that exaggerates the difference between a pixel and its neighbors, which makes all the edges just pop.
Okay, look at this. On the left, we've got the original. On the right, that's the result after applying a sharpening kernel. Just look at how the lines of the car and the texture of the road become so much clearer, so much more defined. And that's all from a simple little 3x3 grid of numbers doing its job.
And now for the complete opposite effect. It's the same convolution process, but this time with a blur kernel. It averages all the pixels, softening those harsh waves and giving the entire image a much smoother, gentler feel. All of that just from changing a few numbers in our little recipe.
Now, this one simple idea, a kernel sliding across pixels, it isn't just for resizing photos and making cool filters. It is, and I'm not exaggerating, one of the absolute cornerstones of all of modern computing. We're talking everything from your phone to the most advanced artificial intelligence.
Seriously, this technique is everywhere. It's the magic behind every single Instagram and Photoshop filter for sure, but it's also used to enhance medical MRIs, to help doctors find tumors. It sharpens satellite photos. And maybe most importantly, it's the fundamental operation that lets a self-driving car see the edge of a road, or allows an AI to recognize a face in a crowd.
And the sheer scale of this is it's mind-boggling. To process a high-definition video in real time, your computer or your phone is performing thousands of these convolution operations on every single pixel, every single second. It's an absolutely incredible amount of math, all happening completely invisibly right in your hand.
So let's just bring it all home. We started with this blocky, broken image, and we found this beautiful, elegant solution hiding in a simple grid of numbers. And that idea, convolution, it taught the computer not just how to resize a picture, but how to truly see it, to find its edges, its textures, its features. So it kind of makes you wonder, if a simple grid of numbers can do all that, what comes next? What else can we teach a machine to understand, starting with nothing more than that?